And in computer graphics, you always come across this term called level of detail. And essentially, it's about scaling up this level of detail, which you see progressively as you zoom in, right? You get to see more details. And this is quite a classic thing in computer graphics. But when it comes to generating stuff with 3D, we believe in a slightly different perspective, which is more useful when you want to do so with LLMs. So you see, like most of these AR models, which is autoregressive models, which is your LLMs, they're going to generate things which is token by token. And this creates a problem, right? Where you see that, for example, when you want to do this with OGGPT, which is a popular model, it takes so many tokens, almost 250K tokens to generate a very simple penguin, or in the case of London Bridge, it's 370K. And this is, again, similar with another popular one called Vertex Regen. And it's essentially doing this because for every single triangle, it is kind of occupying one token, right? And this creates a problem because in the world of LLMs, you've heard of the term called attention, and that is a quadratic complexity, right? So this quickly blows up, and it's also like the more tokens you generate, it's harder to keep context, particularly in the later tokens. So what we want is a slightly different approach where we want, even at the very early stages, we want a complete and recognizable shape. It may not be the exact shape that we are looking for, but we want to do so in a very semantic way, where it at least, let's say, represents the same category that you're trying to generate. So maybe, let's say, you want to generate a Mickey Mouse, but at first, let's say, it's at least looks like a mouse. It may not be that exact Mickey Mouse that you're looking for. And this is an example of generating a 3D shape, token by token, where you can see new triangles are being added with every single token that is being appended to this. And you can see this is a very slow process, and especially at the beginning, it kind of generates a very rough scaffold of the object, which makes it very hard to actually recognize. And if you scale this down even lower, you'll see that you'll just get like some flat triangles, and it's impossible to identify this is actually a cat. So we want to go away from this level of detail into what we call as level of semantics. So, and I'll tell you why exactly LOD is a bad fit for AI generation. So in terms of classic graphics, it was kind of essentially made for rendering and not for generation. And as you can see, you have so many tokens that you need to generate a very simple object, which is completely unrecognizable in the early stages. So in this paper, what we explored is how we can use semantics to actually generate completely recognizable shapes from very few tokens. And we are going to do so by ordering it using semantic salience, so that even very few tokens at the very start actually represent a complete object. And in this way, we are actually going to be extremely efficient and reduce our token usage down to just 0.1 to 10% compared to other models. So this is our comparisons, and this is where we fit in, as you can see. So over here, we can actually generate a complete penguin using a single token alone. And this is way more efficient than previous methods. And I'll point you a very interesting use case where you see that there is this adult penguin, and along with it, there is this baby penguin. So if you want to generate both of these penguins together, let's say, but if you have a single token, and that's your entire budget for generating that shape, it might actually be better to generate a complete penguin, but a single one, rather than trying to get two over here and make something which is completely unrecognizable. So over here, with 4 tokens, let's say we have a good enough penguin. It's single penguin, but it's a completely recognizable penguin. Whereas this, for other methods, they're trying to get both in, right? And they're trying to actually mess things up by making this weird shape down at the bottom. So the idea is to get complete recognizable shapes by using semantics. And for this second example here, you can see with the London Bridge, you see that we generate a very different bridge. But again, this is actually a bridge, right, at the end of the day, whereas compared to something like this, where you can't really understand what it is. And you see that it progressively gets closer to the geometry. At first, it's all about semantics, and then it actually gets both semantically and geometrically closer to our target shape. And you'll see that the only difference between the 16 and 64 tokens is the change in the arc at the very bottom. So we are actually inspired from this work called FlexTalk, which did this for images. And you can see that compared to generating images normally, it again does so in a semantic way. I'll quickly give you a recap of this paper, and I'll tell you what are the challenges of doing this in 3D. So the way this paper works is that you have the classic diffusion pipeline. So you pass your image with a VAE. So you move this into the latent space, and then you are going to encode this image again with some register tokens. Just think of them as learnable tokens, right? So this is an encoder, and there are some tokens that you want to learn to represent this image. And then at the very end, you have a generative decoder. So this is, again, a diffusion model, which conditioned on these set of learnable tokens generates a complete set of tokens back again. So, and in the middle of this, you see the concept of doing nested dropout. So once you pass through this encoder, we are going to drop out tokens progressively. So essentially, it means that, let's say this complete image is 512 tokens. So at first, we are going to keep 1 token, and then 2 tokens, 4 tokens, 8 tokens, 16 tokens with powers of 2, essentially. And what this kind of does is that it pushes all of this information into the very first tokens, because the first token is always going to be kept. So it naturally kind of orders this information to be packed right into the front tokens. So the first token actually carries the most information, and the second token carries a little bit lesser, and so on, where it tries to get more accurate with instance-specific details towards the later tokens. And since the first few tokens are always kept, you can actually represent the category of that image or object quite well with just the first few tokens. And a crucial part of this paper is to actually use the semantics to drive this kind of generation forward. And to do this with images, it's actually quite straightforward, because you have very powerful foundation models for images, such as DINO, or even like diffusion models, which have a lot of semantic information. And with DINO, this paper, what it does is something called representation alignment, which essentially tries to bake in most of these inductive biases which are present in DINO right into the generation model itself. And in general, representation alignment is quite useful because it reduces training time by orders of magnitude by actually using some of these inductive biases present in foundation models. But particularly for this paper, it is more than just reducing the time, because it is actually driving this kind of generation possible, because it is using these semantics to actually bake in what these first few tokens should be capturing. But the problem is that there is no such foundation model for 3D which makes this possible. So I'll quickly describe our architecture, and then I'll go on what is the main problem that we are solving. So we keep most of this architecture. We make some straightforward changes. First of all, we move to the 3D representation. So once you have an object, which is typically a mesh, we are going to represent that in the latent space. And in this paper, we show with different kinds of 3D VAE latent representation. So this is an architecture that is quite flexible, and it is totally dependent on what kind of VAE that you want to choose. So we show this with 2 popular versions of 3D representations. One is called Trellis, you might have heard of, and another is with Direct 3D. Most of these visualizations which I'll be showing in this presentation is with Direct 3D, but we also have some examples with Trellis, which you can find in the paper. So cutting short, once you have this object, which is a mesh, you get the point cloud in, and then you're going to pass it through a 3D VAE to get into the latent representation, just like most generation models. So once you get to the latent tokens, this is where our architecture comes in. So just like flex talk in the for images, we are going to introduce an encoder, and then we have this nested dropout to constantly drop out tokens so that most of this information goes into the first few tokens. And then we have a decoder, which is generative. So this architecture is actually very asymmetrical, and this is actually what powers this architecture through, because this essentially acts as a conditioning token, which when conditioned on this generative model is going to give you the complete set of tokens back, because ultimately you want the entire set of tokens, right? And over here we have the semantic loss for 3D, which makes this all work. So for strong semantics, right, both of these image tokenizer papers use DINO. Now we do not have something like this for 3D. So a naive version of doing this with 3D is like, you have this object, and then you have these 3D latents. You're going to decode this back to 3D. You can do multi-view rendering by capturing this object from different views, and then you run DINO on this and then get semantic loss, right? So this is a popular approach, but this approach is actually extremely slow, because when we want to train this entire network, decoding the latents back into the 3D shape is actually quite expensive to begin with, because you have to do something like marching cube, and this takes quite a lot of time, and then you have to do the multi-view rendering and actually then pass it through DINO, and this is all quite cumbersome, right? So we want to do is that we want to get this semantic loss right back in 3D. And to do this, we have introduced something called as RIDA, which is Relational Inter-Distance Alignment. So let's zoom out for a bit and think what is that we actually need to get a 3D loss in. So what we realized is that ultimately what we need is a loss function that says that, okay, and that if we are trying to generate, let's say, planes, it should say that, okay, this is a plane and this works. And if this is a lamp, it should say, okay, no, this doesn't work, right? But it shouldn't be, penalizing if this is not the exact plane that we're looking for. So in this case, what we actually want is these kind of relationships, and these semantic relationships that are actually captured by foundation models. So here we are actually just going to learn from DINO. And we are going to learn this in a very self-supervised way, which means that we are going to learn this without any kind of labels. So let's say that DINO says that, that all of these four planes, and we're going to trace back to the 3D latent space. So what we want to do is that, let's say this is the 3D latent space that we have, which is highly geometric. We want to modify this 3D latent space such that it actually captures these semantic relationships of DINO. So let's say that, if DINO says that a cat and rabbit should be, let's say, 5 kilometers apart, it should be, we are going to reorganize the 3D latent space to follow that relationship. If DINO says that a kangaroo and a car should be 20 kilometers apart, we are going to follow that relationship. So what matters is that how these distances are aligned in that space and how these objects are related. We are not actually interested in what DINO is capturing, the information it's capturing. We are only interested in the relationships it's capturing. So what we're going to do is reorganize this 3D latent space to follow the relationships of DINO. So let's say we have a large data set of 300K shapes, and we can render some of these shapes with a single view. And then we use DINO as a teacher to have a query. Let's say we have this query airplane, and it will get us some more samples which are positive and negative. So if our query is an airplane, we use DINO as a teacher to find more airplanes in that batch. So and for this we actually need a large batch size. So for training this, it wasn't like crazy setup, but 8 GPUs is something which was quite useful to get a large batch size in so that we can gather a lot of positive and negative samples. So let's say, I think I remember it was something like 768 in terms of batch size. And yeah, once we query DINO, we can get some positive samples and some negative samples. So we can just use cosine similarity to get these kind of samples in. So negative samples can be anything that doesn't look like an airplane. And we just use DINO as a teacher here. And remember, we are using DINO, which is 2D. And that is completely fine because we are rendering them at the moment. But when we use this loss function, we will no longer need to render in the future. So over here, we are doing contrastive loss in a self-supervised fashion, right? So if you've heard of CLIP, which is quite popular, that was also a model which was trained with contrastive loss. So over here, it is essentially saying that positive samples should be kept closer together and negative samples should be pushed further apart. And that is essentially how we are reorganizing our 3D latent space, which is currently highly geometric at the moment. And this is an inference loss, which is essentially going to give us this contrastive setting. And yeah, and other than just getting positive and negative samples, we're also trying to match the similarity matrix of DINO over here. But we do not want to match this directly because our 2D and 3D modalities are different, and we want to respect that. So to do this, we are just standardizing them by subtracting the mean and then dividing it by the standard deviation. Yes. And sorry, that's some weird slides. Yes. But at the end of the day, once we train this network using self-supervised learning with all of these losses fitted in, what we get is a loss function for 3D, which tells us if two objects are similar in a semantic way. And once we train this network, we can actually freeze this network completely and use this as a loss function back in our model. Yes, so this is the semantic loss which we have now trained. And once we train this semantic loss, we can actually freeze this and then train the entire network. So the next time when you're trying to generate a trophy over here and it matches the general category of trophies, it should say that yes, this is a success. And the thing is that because this network was trained completely in the 3D latent space, we no longer need to render anymore. And this makes the training orders of magnitude faster. Yep. And now this, once this network is trained, we can start generating shapes. Over here, you can see that there's quite a bit of variance, particularly during the first few tokens. But as you get closer to, as you add more tokens, you'll see that it gets geometrically accurate to what you want to represent. For example, it can start with a banjo and then get closer to the guitar that you want. But for more simple stuff like an hourglass, you can actually represent it with just a single token because there is not much variation in that. Yep. Oh, and this is a very interesting example. You have this mountain with a face on it, but when you're trying to represent it with very few tokens, of course, a mountain normally doesn't have a face on it, so it tries to ignore that and just tries to represent a general mountain before adding more tokens. So for all of these examples, the first few tokens are always kept. We are only appending. So the difference between the 4 and 16 is that we have added 12 more tokens to it. And the first few tokens are always kept constant throughout, and we're just only appending one by one in an AR native way. And once we have this representation, we can actually train an AR model. We use something like LlamaGen, and we are going to condition the 3D objects on images, so we use CLIP for that. You can see some of these generations with AR models. And you can see the image on the left and the generated 3D object on the right. And we can stop anywhere in this process, right? So if you have a low token budget, you can just stop at 4, 16, or whatever. And compared to other models, we are not only efficient in the number of tokens, we are also efficient when it comes to token dimension. So if you multiply them, we are orders of magnitude more efficient compared to millions. We are there in something like 4096. And because we can also stop anywhere between 1 and 4, this can reduce even more. These are some numbers which are boring, which I'll skip. So one of the more interesting side effects of training this 3D loss was that we actually get shape retrieval for free. So over here, we have this query of a submarine, but it's actually quite confusing because it's shaped like a shark, right? But this is actually a submarine. So when we try to do this retrieval in the geometric space, which is the original 3D latent space, you see that this actually just fetches sharks instead of what we want, which is a submarine. But DINO is quite smart. It knows semantics, so it actually fetches submarines. But once you map those geometric latent space into our latent space, you see that it actually starts retrieving submarines again. So this network that we have trained can do multiple things. This representation is actually quite powerful, besides just using it as a loss function. Some more boring numbers, we just show that it works. And over here we want to show why our RIDA was actually useful during this training setup. As you can see, especially for a very low number of tokens, where we are trying to generate a hat, if we do not use this semantic loss function, it can actually completely get the category wrong and come up with a cup rather than a hat. So, and there are some other examples of a kangaroo where it kind of looks unrecognizable, and we show why this loss function is actually important. Some more boring numbers, and now you have a project web page where you can browse and see more of our paper. Thank you so much.